Okay, so someone had questions on the homework problems, so let's look at a couple of them. How about the first problem, number 3? Okay, there's two problem number 3s. How about the first one then? Okay. Let's get this thing right a little more. Okay, so the first problem, number 3. It goes like this. Let G be a group, P be a CeeLo P subgroup of G, okay, and N be a normal subgroup of G, okay? Prove when you intersect the P with N, you get a CeeLo P subgroup of N, okay? So that's the question. Prove P intersect N is a CeeLo P subgroup of N. Okay? So let's prove. Now you got to start to learn to use CeeLo's theorem. Okay? And not just write down and watch these videos and write down all these proofs, but learn to start to use CeeLo's theorems. That's why we prove them. Okay, so let's prove them. And in this, we'll use CeeLo's theorem several times. Okay. So let's prove them. Okay. So I know P intersect N is in N. It's a subgroup of N because when you intersect two subgroups, you always get a subgroup. That's abstract 1. So I'll say that first. So now P intersect N is certainly a subgroup of N. Okay? Moreover, it's a P group because it's also a subgroup of P, and P is a P group because it's a CeeLo P subgroup. Its order is a power of P. In fact, the P's part of G. Okay? So let's say that. Moreover, P intersect N is a P group. Okay? So now I can use CeeLo's theorem that says every P subgroup, so P intersect N is a P subgroup of N. Okay? It's a P group and it's inside N. It's a P subgroup of N. So I can use CeeLo's second theorem, 468, that says every P subgroup is inside a CeeLo P subgroup of that group. I'm not using it on G, but on N. Remember, you proved that theorem for any group. So now we're not using it on G, we're using it on the group N. Okay. So I know P intersect N is in a CeeLo P subgroup of N. I'll call it, I have to give it a name, I'll call it P0. So by 468, there exists a CeeLo P subgroup of N. I'll call it P0. Such that P intersect N is a subgroup of P0. Okay? So I get this. Okay? Now I start looking at P0. P0 was a CeeLo P subgroup of N. That means it's a P group. And it's a subgroup of N, so it's a subgroup of G. So it's a P subgroup of G. So I can use this theorem, 468, CeeLo's theorem, again on P0 in relation to now G. Okay? So let's say that. Now, P0 is a subgroup of G. And P0 is a P group. So I know it's P0 is a P subgroup of G. So I know by 468 it's in a CeeLo P subgroup of G. Now I don't know that will be this one because it doesn't say which one it's in. It just says it's in one. Read the theorem. We proved it. Okay? But by now 4, 6, 9, they're all conjugate to this one, because G acts transitively on its CeLo P subgroups by conjugation, which we proved in 4, 6, 9. So it's a combination of 4, 6, 8 and 4, 6, 9. Okay? By 4, 6, 8 and 4, 6, 9, and I'll call that conjugate little g. There exists a little g in G, such that P0 is a subgroup of G, P, G inverse. Okay? Now I'm going to start to look at this subgroup, P intersect N. Okay? You know, the subgroup we want to show as a CeLo P subgroup of N here. Now it's time to start to focus on him. He's in several spots right now. And also, now it's time to use the normality of N in a previous problem on this homework set. Okay? So I'll say it this way. Since N is a normal subgroup of G, we have, okay, P intersect N. Where is that? Well, from here it's in P0. Yeah. Yeah, it's in P0. Okay, from here. Yeah, from here, it's a subgroup of P0. But if you look at P0 from here, it's in N, but it's also in this conjugate of P. So it's in their intersection. So that's a subgroup of N, or let's say G, P, G inverse from here. And it's also in N, so it's in their intersection. Okay? But since N is normal, this N is N conjugated by P. Okay? So that's equal to G, P, G inverse intersect G, N, G inverse. Okay? But by a previous homework problem on this homework, I think it was number 2, that's equal to, you can bring the conjugate out. So that's equal to this. Okay? So these are the same because N is normal. Okay? And so you get a very fascinating thing, is if you notice this group on the left is a conjugate of the group on your right. Do you know anything about a subgroup and its conjugate? They have the same order. You proved that on homework set number 2. Let's say that. But the order of P intersect N, the group on your left, is the same as the order of P intersect N conjugate by G, the group on your right. The order of these two groups are the same. So that means every group in this chain of equalities, which there's only 3, there's 1, there's 2, and all 3 of these are equal. So there's, I'll say 3. I'll say it here, 3. There's only 3 groups up here. They're all equal because they're inside of each other and they have the same order. Yeah? This number, the order, and this number. So all 3 of these groups are equal. This one, and this one. Because they're inside of each other and have the same amount of elements. Okay, so in particular, these 2 are equal. So you can say thus, the order of P intersect N is the same as the order of P0. Okay? But remember, P intersect N was in P0. And so, P intersect N is P0. But now remember, P0 was a CeLO P subgroup of N. See, right here. So you can say that final line and the proof is done. Therefore, what, you thought it was going to go on forever? Therefore, P intersect N is that CeLO P subgroup of N, P0. And the proof is done. Put your little box, baby. Learn how to use CeLO's theorem. See how elegant that proof was? Look, it used CeLO's theorem once here. Then it used it again, here and here. Okay, let's do the second problem, number 3. Oh, I gotta get some paper here. Okay, so now the second problem, number 3. Okay? It goes like this. Let G be a group. And again, we're going to have to use CeLO's theorem. Okay? N be a normal subgroup of G. And P be a CeLO P subgroup of N. Prove G is really the normalizer in G of P times N. So if this is true, then every group breaks up into a product of two of its subgroups. Just take a normal subgroup and a CeLO P subgroup of the normal subgroup. And the group is their product of the normalizer in G of that CeLO P subgroup of that normal subgroup times the normal subgroup. Every group breaks into two pieces. Ouch! Let's prove them. And again, the proof is easy if you use CeLO's theorem. Okay? Okay, so these are definitely two sets. So the way to show two sets are equal is show each one is a subset of the other. We don't know the set on the right is a group, because we know we can't just multiply two subgroups and get a subgroup every time. Intersecting them, sure, but not multiplying them, remember? Okay? So I'll just show each one's a subset of the other. Okay? So clearly, anything in this product, something in the normalizer in G of P times something in N, is going to be in G every time by G's closure. Okay? So I'll just say it this way. Since G is a group, in other words, it's closed, we have one inequality. The normalizer in G of P times N is a subset. Don't write subgroup here, because we don't know we don't know this one's a group. Is a subset of G, just by G's closure. I mean, come on, you can never leave the group. It's closed. Okay, so now we just have to show every element of G is a product of something in the normalizer in G of P times something in N. Then we'll have the other inclusion and the proof will be done. Okay, so I'm going to take a random element of G. I'll call it little g. Let little g be in G. And now we have to trap it in this product. Can you trap stuff? I can. Okay, anyway. So we have to trap it. Okay? Now up here we know that P is a CeLO P subgroup of N. So you got to use that, baby. Can't just keep writing this mess. You got to use it. Okay? Can you find another CeeLo P subgroup of N other than this P right here? Another one. Think about it, baby. Are you thinking? How about P conjugated by this little g here? That will stay in N by N's normality here. And it will maintain the same order by a previous homework problem. When you conjugate a subgroup by an element of a group, the order stays the same. So it will still have the order, the pth part of N. So it will still be a CeeLo P subgroup of N. Okay? So that's what I'm going to do. Okay, let's write it. So since, let's say it this way, P is a subgroup of N. In fact, it's a CeeLo P subgroup of N, but that means it's a subgroup of N whose order is the pth part of N. Okay? And N is normal. We get, let's say it in parts, because you might get scared. We get, just conjugate both sides by this little g. We get G, P, G inverse is a subgroup of G, N, G inverse. Okay? But now N is normal, so this is just N. Since N is a normal subgroup of G, we know G and G inverse is just N. So if you replace this into there, right there, follow the arrow, thus we have G, P, G inverse is a subgroup of N. Okay, just replace that into there. Okay? But the order of this is the order of P, which is the pth part of N. Let's say that. Now, the order of this newly found subgroup of N, you have to find it yourself, is the order of P. But since P is a CeeLo P subgroup of N, that's the pth part of N. Start using the notation, baby. That's the pth part of N. And so, G, P conjugated by G, is a CeeLo P subgroup of N, because it has the right order. So all you got to do is have the right order to be a CeeLo P subgroup. And that order has to be the pth part of the group. Okay, remember the notation here? That's the pth part of N, baby. It's a number. It's a power of P. The largest power of P dividing the order of N. Haven't you been listening to the videos? So you've successfully found a second one. We had this one, P. And now we have found another CeeLo P subgroup of N. P conjugated by the little g. See, follow the pen. P, and now P conjugated by G. It's like magic, man. They should call me a magician. Okay, so now it's time to use Ceelo's theorem and whack it, and it's all over now. Anyway, so how do you use Ceelo's theorem? Remember, it says any group acts transitively on the set of its CeeLo P subgroups by conjugation. So these two are conjugate by an element of N, because they're CeeLo P subgroups of N. N acts transitively on its CeeLo P subgroups. Not G, but N this time. And that's 4, 6, 9. Okay, so by 4, 6, 9, there exists, I'll call it a little n and n, such that G, P, G inverse is really N, P, N inverse. In other words, the two in the circle are conjugate by an element of N. Okay, so now I'm going to, okay, so you get that by 4, 6, 9. The one you found and the P are conjugate by an element of N, not G. N acts transitively on its CeLo P subgroups. Yeah? Every group acts transitively on its CeLo P subgroups by 469. That was one of the three things we showed in 469. Okay, so now I'm going to do a little algebra and get the P by itself. So you could say thus. So I'm going to take the N's over there. So you get N inverse G, P, G inverse N is equal to P. Or you can rewrite this thing. This element of G can be rewritten. Okay? Or N inverse little g P, and then N inverse G inverse is P. Because the inverse reverses the order, and the inverse of the inverse is the element. So you get that. Make a big box so you won't be scared of it. See that? Can you tell me what this element is doing to P? It's normalizing it. So it's in the normalizer in G of P. Look familiar? The proof is over. Except you don't realize it yet. So let's keep going. Okay? See, we're in here now. Okay? So let's say that. Hence, since we said thus right there, let's change words. Hence, N inverse G is in the normalizer in G of P. And so it's equal to something in there. I'll call it X. And so there exists an X in the normalizer in G of P such that N inverse G is X. Now solve for G. Why? Because that's what you're trying to learn about. Remember? You let a random thing be here in G and you're trying to trap it. Now you got it trapped. The problem's over. So here is the little g here. Solve for it. So you could say, but then, little g is equal to, take the n over, xn. Now x was in the normalizer in G of P, n was in n, so that's an element of the normalizer in G of P times n. And congratulations, you've trapped the little g that we started with here. Follow the pen. It's that magic trick again. Yeah? So now it's been caught here. That was any element of G. So G is now a subset of the product, and they're equal. Prove the problem's done. But let's write it so we're not scared. Okay? Therefore, G is a subset of this product. And we know the product was a subset of G by the closure, therefore G is equal to it, and the problem's done. So hence, G is equal to the normalizer in G of P times n. And you can put your little square box there. Okay? So try the rest of the problems on your own more before you ask a question. But you can still ask questions. Don't be scared. Okay, but try them more. For number 4, use the hint. For number 4, use the hint. Okay, so you don't have to turn it in today. Maybe turn it in next week. Maybe turn it in next, I don't know, Wednesday. Okay, give you a few days. Simmer on it. Let's say it this way. Try to do the rest of the problems. Keep trying. Use the hints. Yeah, you see that? Put a big arrow there. Put a big arrow there. And if you can't get them, maybe give yourself, what's today, Friday? Give yourself 2 days. So if you can't get them, then Sunday, ask me again. Okay? Okay, so let's write the other thing, because people don't follow instructions very well. Turn it in next Wednesday. Turn in next Wednesday. Okay? On Sunday, ask me a question. Give yourself 2 days to try it, and ask questions starting on Sunday. On Sunday, you can ask questions. Okay, so give yourself 2 days to try it again. Today's Friday, tomorrow's Saturday. Give yourself those 2 days to try it again. Okay, so try number 4. Use the hint. Try it again. Okay? And on Sunday, then you can start to ask questions again. But give yourself 2 days to try them again. Okay. With that being said, have fun and keep doing your homework, because that's what it's all about. Stay safe and keep loving group theory. Go over these proofs, the 2 problem number 3s. Okay? Be able to prove that blindfolded. With that being said, have a good weekend. Remember, today, tomorrow, give the problems another try. And on Sunday, ask me again if you can't get them, because they're very important. You can see we're using Seelos theorem like wildfire. I mean, you can't do that, then do you even know Seelos theorem? Okay, so be careful to make sure you really are digesting these proofs. So watch the video several times. Then prove the 2 problem number 3s on your own again and again, so you get used to using Seelos theorem. It's a massive weapon. With that being said, adios, and keep loving group theory.